All right.
Yeah, go ahead.
Okay, so today we'll talk about policy gradient. So this is outline of today's talk. I'm going to recap some the paradigm of reinforcement learning and something about DQN we talked about last time, and then I'll introduce you some basic concepts for developing the policy gradient algorithm, and then I'll just go into the math. And to derive the world's first policy gradient algorithm, which was published in 1999. And then I'll talk about some implementations with PyTorch using on discrete and continuous action space, just some really simple implementation detail. And I'm going to talk about why reinforce the algorithm won't work well in many problems. And then I'll provide you some further writing, some advanced topics, and conclude the talk. So let's recap the paradigm of reinforcement learning. So in reinforcement learning, we have an agent who interacts with the environment, and you will get the state, or sometimes called an observation, from the environment. And to interact with the environment, it then will takes an action based on the observation or state. And after that, the environment will return a reward. Most of the time, it's just a scalar and a new state. So the objective of this RL problem is to maximize the cumulative rewards, and it is the return. So this is our objective in reinforcement learning. So what we represent, what the agents will learn is there are three things, can be three things. The first one is a policy, which in a more general way, is a distribution over actions conditioned on the state. Or it can learn a Q function, which is the values, is the Q value, action values of a state given an action. Okay, so this is basically equals to the return from the current time step to the future. Or it can also learn a model. Okay, the model is something. The model relates to the environment. It's not part of the agent. So basically, people learn a model to do planning. So this is kind of a general paradigm for reinforcement learning. And last time we talked about deep Q network. So DQN is an algorithm which represents the Q function with deep neural networks. And for better parallelization, it outputs a vector of values, of Q values for each of the actions. So these are the actions, if you look at the figure here, and the output of the networks will be the Q values of each of these actions. And to get the best actions, it's just followed by a single argmax operation. So DQN works well for discrete action space, and especially with small number of actions, right? So most of the Atari game that are experimented in this Nature papers has like 7 or 8 actions, maybe up to 11, but not many. So it's not that good for continuous action space, because for continuous action space, we need a Q function. We can only get a Q function that outputs one value for a pair of state action, which means if we want to operate the argmax operation, apply it on this continuous action space Q function, we will need some optimization procedure, something like a cross entropy method, or people also used mixed integer programming methods to optimize over the Q value function. So these are two papers. First one is the one that use cross entropy methods, and the second one is the one that use MIP. Okay, so This is a recap of reinforcement learning and deep Q network. Now let's go into some concepts for policy gradient. Well, instead of learning the Q function, we can directly learn a parameterized policy, which means that we learn you can say it's a distribution over actions given state. So if we represent it with a neural network, like shown by the figure here, we just get the input, get the state as an input, and we output the action, all right? Or it could be a distribution over actions because it's continuous. So you can expect something like a Gaussian if you parameterize it as a Gaussian distribution, right? And it can be a multivariate Gaussian, which means you have multiple actions. Like if you have several actions, they are all continuous variables. So the objective is the same. We want to maximize the future reward return, but because we are getting a distribution, so we can only we are to optimize maximize the expectation of our future reward over the distribution of the policy, right? So so the optimal policy in the cases we are having some parameterized policy, for example, by a neural network, well, the optimal policy can be represented by the parameters, right? Like the weight of these networks, denoted by theta. The optimal one denoted by theta star. So we write it in this way: argmax theta, the expectation of the future return. And we note here that the expectation is over trajectories, which means from the start to the end of a task. So a trajectory contains something like this: from the first state, the first action, to the T state and the T action, which is the end. So this is the probability distribution over a trajectory. And it's composed by the initial state distribution, the policy distribution, so this is your action distribution, and the model, the transition probability, which gives the probability of the next state given the current state and action. Okay, and the action is chosen by the policy. So this is a joint distribution, right? We will know that this is something trouble. So now let's simplify the notation a bit. We denote this expectation by J theta, because theta is what we want to optimize. Okay, so this argmax is over theta. Okay, this is some basic concepts or understanding of the policy gradient. Ask questions if you are not clear.